In today's session, we are going to solve a few questions based on basic proportionality theorem. Let us take a look at the first question. In this figure, it is given that PQ is parallel to BC and it is given that PR is parallel to DC. We have to prove these two results. So we have to prove that AR upon AD is equal to AQ upon AB, and we also have to prove that QB upon AQ is equal to DR upon AR. So let us think about how to solve these two proofs. So let's start with the first proof. I have to show that AR upon AD is equal to is equal to AQ upon AB. So somehow I have to correlate these sides. I have to correlate AR and AD. I have to correlate AR and AD with AQ and AB, right? But there is no direct connection between these sides of the triangle. So what I will first do is I will first take up the triangles in which I can apply BPT. It looks like I can definitely apply BPT in triangle ADC. So in triangle ADC I can apply BPT. So I can say that in triangle ADC I can say that RP is parallel to DC, and therefore by using BPT, I can say that AR upon RD is equal to AP upon PC, right? This is by BPT. This is the first result that I obtained. Similarly, there's another triangle in which I can apply BPT. So I'm going to apply BPT in this triangle now. So I can say in triangle ABC, I have PQ parallel to BC, and therefore again by using BPT, I can say that AP divided by PC is equal to AQ divided by QB. This is the second result. And now you will notice that I have AP upon PC in both equations, right? So this is a good connection, or this is a good bridge that will now join the sides that I require. I notice that I have AP upon PC in both the equations. So I can say from the first and second equation, I can say that AR upon RD is equal to AQ upon QB. Now let me take a pause and let me see what I really want. See, I want AR to be as it is. Okay, if I'm now trying to prove the first one. Okay, I'm trying to prove the first one here. So I want AR, I have got AR. I want AD, but I don't want RD. So what I will do is, I will first take reciprocal on both sides. So taking reciprocals, by the way, the idea of taking reciprocals is going to eliminate RD. So let's see how. I get RD upon AR is equal to QB upon AQ. This concept of taking reciprocals is basically called invertendo. So if two ratios are equal, then their reciprocal should also be equal is the concept of invertendo. Invertendo is nothing but if two ratios are equal, then their reciprocals are also equal. Now I want AR and AQ, right? That is why I have taken AR and AQ in the denominator, and now I am going to add 1 on both sides, and let's see what happens because of that. So when I take the LCM of the denominator, in the numerator I get AR plus RD, the whole divided by AR is equal to QB plus AQ, the whole divided by AQ. And if you think about what is AR plus RD, AR plus RD is equal to AD. So I get AD upon AR is equal to, let's consider what is QB plus AQ. QB plus AQ is equal to AB divided by AQ. And again taking the reciprocal now. So by invertendo, what we now get is AR upon AD is equal to AQ upon AB, and this is exactly what we wanted to prove, and hence I say hence proved. So whatever terms are required, we keep it in the denominator, because when you add 1 on both sides and after you take the LCM, you will notice that the denominators don't change. The numerator does change. So AR plus RD became AD. So the numerator has changed, but the denominator does not change, and that is why the terms that we need, keeping them in the denominator definitely works. So we have proved the first part. Now let's think about the second part. QB upon AQ. So if you notice, if I mark this as result 3, I already have AQ upon QB. I just want QB upon AQ. So what will happen if I take the invertendo of the third result? So by invertendo of equation 3, what I will now get is, I will get RD upon AR is equal to QB upon AQ. And if you notice, that is exactly what I need to prove in the second subpart, right? And hence I have proved both the subparts by using BPT. So again, let me pause for a minute, take a look at the different techniques that were used here, and then we will continue with our next question. Moving on to the next question. Let us consider the following question. It is given that AD, the length AD is equal to the length BE. This is given to us in the question. So let's mark it. We have AD equals BE. Also DP is parallel to BC. This is also given to us in the question. So let's mark it. And we have QE parallel to AC. So this is also given in the question. Let us again mark it. Rather, I would mark the two parallel lines with the same color. Okay. Though you should mark it with arrows, I am marking it with the same color so that it can be visually quickly noticed. Now we have to show that PQ. So we have to show that PQ is now parallel to AB. This is what we have to show in this particular question. So let us quickly now apply what we know. We know that DP is parallel to BC. So I can say that in triangle ABC, I know that DP is parallel to BC, which means that AD upon DB is equal to AP upon PC, right? And this is by basic proportionality theorem. So let's mark this with the first equation. Similarly, I know that QE is parallel to AC. So again in triangle ABC, I know that QE is parallel to AC, and therefore I can say BQ divided by QC is equal to BE divided by EA. Again, this is by BPT. This is by BPT, and this is the second equation. Now what I'm going to do is, see, if I want to prove that PQ is parallel to AB, let me just write what I have to prove. If I have to show that PQ is parallel to AB, I have to somehow show that BQ upon QC is equal to, so BQ upon QC is equal to AP upon PC. So if I can show this, then I can use the converse of Vpt to say that BQ is parallel to AB. Now, if you notice, I already have BQ upon QC here. So here I have BQ upon QC. And I also have AP upon PC. I have obtained AP upon PC right over here, right? So now it's just a question of connecting these two equations. So let us think about how can we connect these two equations, and this is where BE equals AD is going to help us. Now let's compare these two ratios, right? AD upon DB and BE upon EA. If we can show that these two are equal, then I can conclude that BQ upon QC is equal to AP upon PC. Now the length AD is equal to BE. So if you consider the numerator, I have AD is equal to BE, and this is already given to me in the question. Similarly, the length DB. So what is DB comprised of? DB is comprised of the length DE and EB. So I can say that AD plus DE. Assume that I am adding DE on both sides. Let's see what is the result that we get. So AD plus DE basically becomes AE. So AE is equal to, I should have replaced this with the addition sign, not with the equal to one, is equal to BE plus DE. Now BE plus DE is actually equal to BD. So I have AD is equal to BE, and I also have BD is equal to AE, right? Now if I divide these two, what will happen? I will get AD upon BD. Therefore, I have AD upon BD is equal to BE upon AE. Let me repeat what we did. We first took AD equals BE. This is given to me in the question. Now, if you think about AD upon DB, think about it. AD upon DB, right? AD upon DB is what we have in the first equation. and we have BE, that is this length, upon EA in the second equation. So what I did was, I know that AD and BE are equal. So the numerators of these two ratios are equal to each other, right? AD and BA are equal to each other. Now I am comparing DB with EA. So if you think about it, DB is composed of two parts. One is DE and the other is the length BE. And BE and AD are equal to each other, right? And that is why I said that AD plus DE is equal to BE plus DE, which is how I got AE and BD equal to each other. So even the denominators of these two are equal to each other. And that is why these two ratios are going to be equal to each other, which is what I have written over here, right? So AD upon BD is therefore equal to BE upon AE. And therefore from 1 and 2, from 1, 2 and 3, let us mark this as result 3, I can say that AP upon PC is equal to BQ upon QC. And since AP upon PC is equal to BQ upon QC, I can say by converse of BPT, by converse of basic proportionality theorem, I can say that PQ is parallel to AB. And this is how I prove this particular problem. So again, pausing for a minute, take a look at the complete solution and then we shall continue. Moving on to the next question. Let's take a look at the following question. It's given that FE is parallel to DC. So in this particular case, that FE and DC are parallel to each other. So let us mark these sides as parallel. And it is also given that DE, the length DE, is parallel to BC. So let us mark DE and BC also as parallel, right? Now we have to prove that AD square is equal to AB into AF. So let's start with applying BPT in these triangles. The first BPT candidate or the first triangle candidate for applying BPT is definitely triangle ADC. So I can say that in triangle, so this is the proof, in triangle ADC, I can say that AF divided by FD is equal to AE divided by EC. This is by BPT, and let this be the first statement, right? So let us mark this as the first statement. Similarly, the next candidate for applying BPT is going to be the whole triangle. So this is the whole triangle. So I can say that in triangle ABC, okay, by the way, I should mention here that FE was parallel to CD. So in triangle ABC, I have DE parallel to BC, and therefore AD divided by DB is equal to AE divided by EC. This is again by BPT, and let us mark this as the second result. So let us mark this as the second result. So one thing that I notice over here right away is I can say that because both these sides contain AE by EC, right? The right hand sides of both equations is AE by EC, and therefore from 1 and 2, I can conclude that AF upon FD is equal to AD upon DB. Now let us compare what all we have in the equation. We have AF, I want it in the final equation. So I need AF in the final equation. I want AD square, so let me preserve this AD as well. I don't want FD, I don't want DB. So if I don't want these terms, then let me apply invert endo. So by applying invert endo, what I get is FD upon AF. Now instead of saying by invert endo, you can also say taking reciprocals. That is also fine, right? Taking reciprocals on both sides. So then I have FD upon AF is equal to DB upon AD. And now what will happen if I add 1 to both sides? So why am I adding 1? I am adding 1 because I notice that AF plus FD will suddenly give me AD, right? And I'm falling short of 1 AD here. Similarly, I don't want DB, but if I add 1, then AD plus DB will make it AB in the numerator. So adding 1 to both sides definitely is going to help here. Adding 1 to both sides, what I now get is 1 plus FD upon AF is equal to 1 plus DB upon AD. So let me explain the rationale of adding 1 again. See, in my final equation that I have, this is what I have to prove, right? In this final expression that I have, I don't have FD anywhere. Correct? I don't have FD anywhere. So if I add 1 on both sides, when I take the LCM, the numerator is going to become AF plus FD, which is actually equal to AD, right? So this numerator will therefore become AD, and that is quite desirable because I want AD square. Similarly, on the right hand side also, I don't want DB in my final equation. But when I add 1, I will get AD plus DB, which is equal to AB, right? And that is why I'm adding 1 to both sides. So after taking the LCM, I will now get AF plus FD upon AF is equal to AD plus DB upon AD. Now AF plus FD becomes AD. So AD upon AF is equal to AB upon AD, and therefore cross multiplying, I get AD square is equal to AF into AB. And this is precisely what I wanted to prove in the given problem. So again over here, using BPT in all possible triangles definitely helped me. And of course, the addition of 1. So when do you know that you have to add 1, or when should this principle be used? This particular principle should be used when you can notice that adding your numerator and denominator is possible. For instance, FD plus AF. So FD plus AF gives you AD. And similarly, DB plus AD gives you AB. So whenever you notice that the numerator and denominator are going to add up to a third length in the given triangle, that is when adding 1 makes a lot of sense. The term that you actually need, so over here I saw that I need AD and I also need AF. The terms that you need should always be there in the denominator, so that even after adding 1 and taking the LCM, the denominator does not get affected, and that is how you decide whether you need to take the reciprocal or not, right? So I will pause for a minute again while you take a look at the proof, and then we will continue with the next question. Moving on to the next question. Let us consider the following problem now. In this triangle, set of parallel lines are given. It's given that DE is parallel to AC. So let us mark these two lengths with the same color. So DE is parallel to AC. That's given to me. And it's also given that DC is parallel to AP. Right? These two lengths are also parallel to each other. Now we have to prove that BE upon EC is equal to BC upon CP. So again, let's pick some candidates for applying BPT. It looks like I can definitely apply BPT in this triangle. So I can say in triangle, so let me start with the proof. In triangle BAC, I can say that BE upon EC is going to be equal to BD upon BA. Again, this is by basic proportionality theorem because I have DE parallel to AC. Now it's great that I have already got BE upon EC, right? So I think we are on the right track, and let us mark this as result 1. Now we need to find one more triangle where we can apply BPT. So let's see another triangle where we can apply BPT, and that triangle happens to be the complete triangle where DC is parallel to AP. So I can say that in triangle ABP, I can say that DC is parallel to AP, and therefore by BPT, I can say that BD divided by DA is equal to BC divided by CP. So this is result 2. Now you will notice that BD upon DA is the common term in both these equations, right? This is the common term that we have in both the equations. And hence I can say that, therefore, from 1 and 2, I can conclude that BE upon EC is therefore equal to BC upon CP, and this is what we had to prove, hence proved. This is exactly what I had to prove, and hence choosing the right set of triangles and writing the right BPT equations quickly gave me the result. So again, pausing for a minute before I move on to the next one. Moving on to the next question. Let us take a look at this following question. In this diagram, it's given that DE is parallel to AQ. So let us quickly mark it. DE is parallel to AQ. And we also have DF parallel to AR. So DF is parallel to AR, right? These two lines are also parallel. We now have to prove that EF is parallel to QR. So again, let's start applying BPT. Let us choose the right triangle. So these are the triangles in which I would like to apply BPT because DE is parallel to AQ. So I can say that in triangle PQ, in triangle APQ, I know that DE is parallel to AQ, and hence I can say that PE divided by EQ is equal to PD divided by DA. This is by basic proportionality theorem. Let me mark this as the first equation. Now I similarly have, so I can now pick the second triangle for applying BPT. This is the second triangle that I have. So I can say that in triangle PAR, I know that DF is parallel to AR, and therefore I can say that PD divided by DA is equal to PF divided by FR. Again, this is by BPT, and this is my second result. So now again in these two results, I notice that something is common. I notice that the ratio PD upon DA is common in both the equations, and because the one term is common in both the equations, I can therefore conclude that from 1 and 2 I can conclude that PE divided by EQ is equal to PF divided by FR. That is, PE divided by EQ is equal to PF divided by FR, and therefore I can say that by converse of BPT, I can therefore say that FE is parallel to QR, right? And this is how I prove this given problem. So again, applying BPT, choosing the right triangles definitely help me prove what I need. Again, I should be always marking the parallel lines, right, in a given problem, and I will again pause for a minute before moving on to the next one. Moving on to the next question. Let us consider the following question. It's given that PS upon SQ, it's given that PS upon SQ is equal to PT upon TR. So because it's given that the line ST is dividing the two sides in the same ratio, so I can definitely apply the converse of BPT, and I can say that ST is parallel to QR. It is also given that angle PST, that is this particular angle, is equal to angle PRQ, right? These two angles are equal. This is given to me in the question that these two angles are equal. I now have to prove that triangle PQR is an isosceles triangle, right? So let us see how we can go about this particular question. I can start off with using converse of Vpt. So let me mark this as the proof. So I can say that since PS upon SQ is equal to PT upon TR, this is given to me in the question, I can therefore say that the line ST is parallel to line QR. This is by the converse of basic proportionality theorem, right? And that means these two lines are therefore parallel. Now because these two lines are parallel, I can say that angle PQR I can say that angle PQR is therefore equal to angle PST by the corresponding angle test. So this means that angle PQR is equal to angle PST because the corresponding angles are equal, right? And it's also given that angle PST is equal to angle PRQ, right? This is also given to us. So from the first and second equation, from equation 1 and 2, I can therefore conclude that angle PQR is equal to angle PST is equal to angle PRQ, and therefore I can say that angle PQR is equal to angle PRQ, and because the base angles are equal, I can conclude that triangle PQR is an isosceles triangle, right? So this is how I can prove that the given triangle is isosceles. So pausing for a couple of seconds before moving on to the next proof. Okay, let us move to the next proof now. Let's take a look at the following problem. It is given that BD equals CE. This is given to us. It's given that the length of BD is equal to the length of CE. And it is also given that angle B is equal to angle C, right? These two angles are also equal to each other. Now we have to prove that. So in this particular question, we have to now prove that D is parallel to BC. So let us start with the proof now. We have BD equals CE. And now if I want to prove that the two lines are parallel, right, I will somehow have to use the converse of basic proportionality theorem. So somehow I have to show that AD upon DB is equal to AE upon EC. If I can show that, then I can say that the two lines DE and BC are parallel to each other using the converse of BPT. So now let us see how to go about it. We know that angle B and angle C are equal, right? So angle B is equal to angle C, and this implies that the length of AB should be equal to the length of AC because the base angles are equal, and this implies that the triangle is isosceles, right? So now I have the total length AB. I have the total length AB equal to the total length AC. These two lengths are equal. And it is also given to me that the length of BD is equal to the length of CE. This is also given to me, right? And therefore I can say that I can subtract these two, right? I know that AB is equal to AC. I also know that BD is equal to CE. Therefore I can subtract these two equations. So AB minus BD therefore becomes equal to AC minus CE. Now what is AB minus BD? AB minus BD will be equal to AD. Therefore I can say that the length of AD is equal to AC minus CE is equal to AE, right? And therefore the length of AD and AE is also equal, and this therefore means that triangle AD is also isosceles. Now I know that AD is equal to AE. I also know that DB is equal to EC, which implies that if I divide these two equations, I get AD upon DB is equal to AE upon EC, and therefore by converse of BPT, I can say that the length, the side DE is therefore parallel to BC, right? So over here, the concepts that I used were, first, I used the base angles of a triangle are equal imply that it is isosceles. That was one concept that I used in this particular problem. Then I also use Euclid's postulates, that if you subtract equals from equals, you get equal measures, right? That's another idea that I used here. And then of course, if two quantities are equal, then the ratios should also be equal. That is the third idea that I used in this particular question. And then of course, converse of BPT helped me prove the given problem, right? So this is how I solved this particular question. Let me again pause for a minute before I move on to the next one. Moving on to the next question. Let us solve the following problem. It is given that in this question, PQ is parallel to DE. So let us mark the parallel lines with the same color. This is just for easy visual reference. So these two lengths are parallel. It is also given that PR is parallel to DF. So we have PR parallel to DF. So these two lengths are also marked with the same color, just for visual reference. Now we have to show that QR is parallel to EF. So first let us join QR, okay, and we have to show that QR is parallel to EF. So again, let me now choose my right triangles for applying BPT. I know that in these triangles, in this triangle I have PQ parallel to DE. So I can say that in triangle, let's mark this particular point as X. In triangle DEX, I have PQ parallel to DE, and therefore I can say using BPT, I can apply XP divided by PD is equal to XQ divided by QE, right? This is the first equation that I have. Let us mark this equation. Then let's consider the other triangle that can be a valid candidate for BPT. That happens to be triangle XFD, in which PR is parallel to DF. So I can say in triangle XFD, I can say that XP upon PD is equal to XR divided by RF, right? This is again because PR is parallel to DF, and again using BPT I can write this particular statement. And now if that's the case, then I again notice that I have two equal quantities. I have XP upon PD in both the equations. So I can say that since both the equations have XP upon PD, then I can say that from 1 and 2, I can say that XQ upon QE is equal to XR upon RF, right? And therefore by the converse of Vpt, I can say that QR is therefore parallel to EF, and hence I have proved what I wanted to do. So again pausing for a minute before moving on to the next one. Moving on to the next question. Let us take a look at the following question. PQRS are the midpoints of the sides ABCD of any quadrilateral. So ABCD is some random quadrilateral, and PQRS are the midpoints. So midpoints would mean that the length AP is equal to PB, then BQ is equal to QC, and I also have RC equal to DR. R is the midpoint of DC, and similarly SD is equal to AS, right? I have to show that PQRS is a parallelogram. So I am thinking of how to apply BPT to solve this particular question, or the converse of BPT. I have joined the diagonal AC. So now is it possible for me to apply the converse of BPT in this particular triangle? So if I think about it, I can say that I know that ds upon SA is equal to 1, and similarly dr upon RC is also equal to 1. Why is it equal to 1? It is equal to 1 because the lengths of the sides are equal to each other, right? And therefore this implies ds upon SA is equal to dr upon RC, and therefore by converse of BPT, I can therefore say that SR is parallel to AC. So let us mark this as the first important result that we have got. Now let me take the other triangle where again I can apply converse of BPT, and that happens to be the triangle ABC. So I can say in triangle ABC, I again have BP upon PA is equal to 1. Similarly, BQ upon QC is also equal to 1. And this implies BP upon PA is equal to BQ upon QC, which implies that PQ is also parallel to AC, again by converse of BPT. Converse of BPT, and this is my second result. So now if you notice, you have PQ parallel to AC and AC parallel to SR. So this implies that SR is parallel to PQ. So this is the first result that I have obtained. I have obtained that the opposite sides of PQSR are parallel to each other, right? This is the first result. Now similarly, let me do one more thing. Let me again join the other diagonal. The other diagonal is BD. So now again I can consider some triangles here, right? I could consider the triangle, I could consider triangle BDC. So again in BDC you notice that CR upon RD is equal to 1. So I get CR upon RD is equal to CQ upon QB is equal to CQ upon QB, which again means that RQ is parallel to BD. Again, this is by converse of BPT. So from this result, let me write this result here. So I have CR by RD equals CQ by QB, which again implies QR is parallel to BD, again by converse of BPT. And similarly, I can also take up the triangle ADB, right? I can take the triangle ADB. So I can say in triangle ADB, I can say that AS upon SD is equal to 1. Similarly, AP upon PB is also equal to 1. And this means AS upon SD is equal to AP upon PB. And this again implies that SP is parallel to BD, again by the converse of VPT, converse of VPT. And therefore I have SP also parallel to BD, right? And now you will notice that in quadrilateral PQRS, both pairs of opposite sides are parallel. So in PQRS, we notice that PQ is parallel to RS and PS is also parallel to QR, and both pairs of opposite sides are parallel, which implies that PQRS is a parallelogram. So of course, we could have also proven this property using the midpoint theorem because we have midpoints over here. But I wanted to show you that you can prove the same property using the converse of BPT as well, right? So this is how we solve this particular problem. I will pause for a minute and we end our today's session over here. Take a look at the different strategies that were used in this particular problem before we end our session. Ending today's session here.